My name's Erich Gunther with EnerNex Corporation. I'm the Chairman Chief Technology Officer at EnerNex. We're an electric power engineering research and consulting firm. Happen to be working in the smart grid arena a lot right now. My background is an electric power engineer, but I also have a heavy background in enterprise architecture, utility communications, and the like. Basically, I oftentimes get introduced as someone who speaks geek in multiple languages. So which happens to be an important characteristic for smart grid today. Now, what I'm going to talk about today is to provide a little bit of overview of the use of internet technology, specifically TCP, IP, and other more advanced protocols in utility automation from 5 years before Google and earlier. So I'll occasionally refer to my BG and AG timeframes for before Google and after Google. So BG and AG. The first thing to note that for utility automation, what we're dealing with here are a convergence of at least two infrastructures. I can argue more, but we at least have two infrastructures we have to deal with. We have the existing electrical power infrastructure, the lines you see along the road and in the fields, between cities that connect central generation stations, substations over long distances to distribution stations, the small fenced-in areas with smaller equipment you see in cities. And that then emanate out along feeders anywhere from a few miles to 40, 50 miles long, to where the loads are located. So a significant physical infrastructure we've had in place for over 100 years, in one form or another, very similar to what we still see today. That physical infrastructure, however, has been overlaid with some time by a communications infrastructure. It's a matter of the level of sophistication of that infrastructure that determines whether we want to qualify it as smart grid or not. But for a number of years in the history of electric power management, we have been using communications command and control to manage the these assets on the electric power infrastructure. I could spend a couple of days talking about the various standards and protocols that are used in this infrastructure, and the shortest I usually can do it is in about a day, but I'm going to try and do it in an hour here. But this diagram here, gives you an idea of the different standards that are involved, the different domains of utility automation. We've got the back office, the enterprise, for which we need to have protocols, information exchange, networked communications. The control center, sort of a specialized element of the back office enterprise. Getting out into the field through wide area networks of a variety of different technologies to connect to those various substations and other assets that are distributed all over the country where the devices are actually located. Then getting into the local areas, what we like to call the field area network, providing us the connectivity to commercial end users, to consumers, residential end users, to bulk generation sources, to all the various substations that are out there, to distributed resources. So all of these different elements need to have some level of connectivity for the most basic operation as well as the most advanced operation. Where I'm going to be able to show you is that to a large extent, IP is already pervasive in all of these. So in the news and the like, sometimes the utility community is portrayed as being a bit backward and, gosh, why don't they just use IP? Haven't they thought of that? Well, the answer is yes. It's been in place for quite some time. It just hasn't been exactly all that well known and as sexy as some of the interesting uses of IP that you guys are responsible for putting together here. So I'll give you a little bit of background of what's been done and some of the reasons why, which will point to some things that we can do and bring new innovation moving forward. Well, why automation in the first place? Now, certainly 100 years ago, we didn't have communications like this. We relied on automation, but mechanical, entirely local, no communications. But what really drove automation? Well, a couple of key events really drove that. Starting in the 60s with the Northeast blackout of 1965, that led to a whole lot of different efforts to change the way that the power system is managed, how we measure reliability, the standards we have in place, the need to automate, to understand how the various protective devices interact. It was the a defining event that resulted in the creation of the Electric Power Research Institute, EPRI. That was reinforced in 2003 when we had another widespread Northeast blackout. And it uncovered a whole series of new areas where we weren't communicating as well as we should, human communication as well as machine-to-machine communication. And I can trace a path and have in other talks that can show that August 2003 blackout was, I think it was actually August 14, but contributed to what became the Energy Independence and Security Act of 2007. Prior to that, the 2005 Act that had states look at smart metering. So a lot of it, I can say, started from this event. So historically, in the utility automation, we've been dealing with mechanical devices that have worked just fine. They're very intelligent devices in their own, small mechanical computers, if you will, that perform very specific functions very reliably with little or no maintenance for many, many decades. And some of these, you can walk into some substations in the country and find some of these still in place today and working just fine. But there was a observation that we can use technology to make these devices be more cost effective and operate in more innovative ways as we apply microprocessors and other technologies. So, in the 70s, we started adding electronics to automate these devices, which then led to being able to connect them. So today, and we use the term protective relays, probably the most common intelligent devices in the grid today are the devices that keep the grid safe, keep things from blowing up, keep transformers from blowing up in your neighborhood, make sure that if someone or something contacts a line, it very quickly is de-energized, and we call those protective relays. But they're some of the most intelligent things in the grid, and if they misoperate, has the most significant opportunity to disrupt the grid if an adversary gets in or something behaves incorrectly. So since the advent of cheaper communications, cheaper electronics, there's been an explosion of intelligent electronic devices. Pun intended on the if you notice the acronym that we use. For these devices is the IED, and in our world, utility world, we invented IED before the terrorists did. So I'll be using the term IED, quite a bit, here during this discussion. The general concept of managing devices on the power grid that is generically internationally called telecontrol, but in North America we generally refer to it as SCADA, supervisory control and data acquisition. This evolved to take advantage of these new electronic devices, find ways to remotely control them, monitor their status, change their configuration, and this was done with very specialized protocols for performing utility operations. The characteristics of these protocols were very dependent on this long-lived history of how the mechanical devices evolved, electronics were brought into play that mimicked the mechanical behaviors, added on to them, and so a lot of the way things evolved were because of the long history and long-lived nature of the devices in the field. So I'm going to cover a few of these, talk a little bit about the multitude of protocols that we started off with and where we've been moving towards here recently. So in the beginning, we really did have the Tower of Babel. There's 100 or so vendors of different types of equipment. Every vendor, had a protocol. It just seems like a rite of passage that if you're a new engineer in a new project, by gosh, you got to create a new protocol yourself. I don't know any engineer who hasn't done it at least one time before they finally realized after a while that that's probably not the best thing to do. So that was done. In those days. Was trying to encourage brand loyalty, or we now call it vendor lock-in, in order to get the business with a particular utility or infrastructure provider. Huge investment was made in the SCADA master stations. That's where all the money was. So it was to the vendor's advantage to lock the utility in to that particular master by using their own protocol to the end device. So data concentrators then were created within the substations in order to talk to all the other devices. So we early on had a multitude of, and still today, of data converters in order to provide our well-defined points of interoperability. This is just a partial list. The full one takes many pages of the SCADA protocols that were out there. Many of the protocols are named after the utilities that invented them. Okay, so AEP protocol, PG&E protocol. Okay, that was one of the earliest ones. But a whole host of different protocols. Some specific to utilities that invented them. Some to computing companies, large equipment manufacturers, ABB protocol, for example, and others. So we've had a lot of them. And given the long-lived nature of the utility infrastructure, a lot of these are still out there. But they're collapsing pretty rapidly, to a few that I'm going to focus on, here now. But if we go back and we look at, around 1980, and we're trying to do this, automation and replace the electromechanical relays and other field equipment with electronics. We were talking about 8-bit processors. 9,600 bits per second was considered, really fast. For the most part, 300 baud, was plenty fast enough and actually for some things today it still is. Memory was very expensive. We didn't really have anything in the way of radio, so we were using mainly leased serial lines for everything. The case to automate, the business case, was unproven. Some say it may still be unproven. Basically you had the mechanical device that everyone understood and knew, or this newfangled electronic thing that maybe could communicate, and they wanted to spend the same money, with it. As the two. So the fact the cost pressures made it very difficult for those new electronic devices to be very sophisticated. So very processor constrained, had to be brute stupid, cheap in order to produce. In the same context, our connectivity was essentially phone lines, leased lines, dial-up lines, very poor quality because the radios were still too expensive. Hadn't even thought about LANs yet. Power line carrier was used early on. That was one communication mechanism that was used. But the earliest protocols that were developed were not reliable. They couldn't compensate for the noise on these things. So a lot of the protocols evolved to some very arcane implementations in order to get around these issues. Some major failures early on really caused a lot of paranoia, and things then got overbuilt and overbuilt and overbuilt with extra and more redundancy, built in. A good thing in general, but done it wasn't engineered. It was just done. Starting in the mid '80s to early '90s. Big customers were tired of the vendor lock-in, looking for reuse and standardization. We were starting to get new protocols being available, things like this newfangled thing, TCP/IP, and other advanced protocols. Users groups were beginning to form to band together as utilities and infrastructure owners to force the vendors to try and get some standardization in place. We still had some limitations, a lot of limitations, still not much bandwidth in order we had more ideas than we had enabling technology to be able to allow us to cost effectively implement. So really, moving into the early '90s, so 5BG, 5 years before Google, 1993, SCADA discovered the local area network, and that's where we really started to apply it. Now, a lot of people, thought, don't you mean 2003 or 2005? I mean, you were starting to use local area networks and TCP/IP in '93? Well, yeah, we were. And a number of things, were driving that. Office computing was starting to spread in the SCADA world. We had engineers who were using office computing networks, and they wanted to go and try and put that in the substation because they can. So we had more CPU memory bandwidth was available. A couple of other drivers. In '93 we had the National Information Infrastructure Initiative that Al Gore was involved in, and an outcome of that was a Department of Energy grant specifically designed to use internet protocols for energy applications. And a lot of folks aren't aware of that project, but it was sort of a groundbreaking effort to specifically look at how to do that. And the screenshots I have here are from the first implementations of that, using an old Netscape Netscape browser and an early Internet Explorer browser in '95 to query data, in this case from NASDAQ. Pulling back energy usage information, power quality event information in the 90s, in 1995. One of the main things that had to happen, we tried doing this a little bit earlier, but getting reliable TCP/IP stacks to work in embedded systems was very difficult to find at the time, and operate for more than a day before rebooting, memory leaks, all that happy stuff. So that that was a challenge early on. We started to be able to discover that. The big problem that we still had in those times was reliability and robustness in a non-office environment. We had folks developing office equipment that had its own reliability in the office environment, let alone putting something in a substation for which, when there's a problem on the system, thousands of amperes of current flow causing electromagnetic interference that would just totally blow the brains of most any equipment that would be used in an office environment. So that was a challenge. These SCADA protocols were very simple, memory mapped, register based. The meaning was related to a physical memory location, a specific bit pattern, no concept of layered systems, loose coupling. This was incredibly tightly coupled, programmed to the bare metal, if you will, in order to scrape out every ounce of performance. And all sorts of innovative, crazy things were done in order to get the information from point A to point B with very low overhead, because again, things were still very, very expensive. So once we got beyond that proprietary stage, we started to get some coalescence around the concept of developing some protocols with some more modern computer science and communications theory applied to it. Early protocol that's still around today called Modbus was very widely used in industrial automation, but some very basic concept of being able to set a variable and get a variable. It was patterned after physical manifestations. So when you look at the terminology, you'll see registers referred to as coil registers or input registers or holding registers. It still had mapping to the physicality of the devices that were there. So it's still very, very tightly coupled. So we had some of these early protocols, but there was no standard for timestamping the data. One thing that you do mechanically in an electric power infrastructure is you want to select something first, basically, okay, prepare the device so that we're ready to operate it. Once we make sure that, yes, in fact, we know this is the device we're going to operate, then you operate. So called select before operate. These early protocols didn't have that, and there were some rather spectacular failures when an addressing scheme inadvertently addressed the wrong device, and instead of opening this breaker, it closed the other one and caused a massive failure. So some key features were missing in these early elements, but they did survive, and that protocol has evolved to operate over TCP/IP. But it doesn't have any inherent built-in security, and it is not very extensible. The protocol that evolved after that is one that's probably still the most pervasively deployed in the world today, especially in North America, DNP3. It was developed by a company called Westronic, which later became a part of GE and GE Harris. It was based on some early IEC, International Electrotechnical Commission Act work in Europe to develop a protocol, but they weren't interoperable. That evolved over time to create a users group. It's now being standardized in the IEEE, and is really sort of the workhorse today of remote terminal unit intelligent electronic device communications, mainly again in North America, South America, Australia, Africa. Popular in the water world as well. It's robust enough. Its design was good enough in that we had communications engineers working side by side with the power engineering domain experts, that we started to get some things into it that allowed it to be more extensible and long-lived. supporting various mappings to underlying physical layers. It lent itself to being able to create a TCP/IP-based implementation, and we were able to put a security in it at a relatively low level of the protocol. So very reliable, still still more register based. It doesn't have an information model per se. You still, vendor A and vendor B. Vendor A may represent voltage in register number 23 and represent the units in volts, but vendor B may put voltage in register 47 and it may be in kilovolts. So still quite a ways away from the kind of interoperability and self-discovery we see in other protocols in other industries. The final evolution was to the 61850 protocol family, which was sponsored by the Electric Power Research Institute, starting in the late 80s, leading up to a specification in 1992 that really merged fully the information technology community, computer science folks, and the power engineers with their domain expertise to come up with a pretty elegant system that supports these architectural concepts of layered systems, loose coupling, and the like, and the concept of an information model. The problem was in the mapping of that abstract model that was very well done. The physical manifestation to the MAC-PHY layer was pretty poor. Serial was the primary mapping, no TCP/IP support, but it was focused on what was very popular at the time in the federal government, the full ISO network stack implementation, competing with TCP/IP at the time. So not a lot of pilot projects, a lot of pilotitis, but no consensus. But there's nothing like a real project to focus the mind and actually get something done. So American Electric Power had a need to replace some of their already aging infrastructure, being a utility with one of the older utilities. They needed to replace some equipment, so they had an initiative to bring some focus to it, which resulted in taking the best of what was done before and creating a TCP/IP support to the protocol via RFC 1006 that maps the ISO stack to TCP/IP. That was published as an IEEE standard first as a mechanism to transfer it to the IEC, and within the 2004-05 timeframe, the various parts and subparts were then finally standardized as what we know as 61850. And that's probably the leading standard for new implementations today. Definitely in the rest of the world, we're a little slower in the US for a variety of reasons. In most of the rest of the world, standards are treated more like law. Once a standard is available and applicable, pretty much right from the get-go, a new installation is going to use it. That's how they're treated in the electric power industry. In the US, all of our standards pretty much are voluntary, and so even new installations today are still implementing some of the old stuff because we just don't have a mechanism to mandate or do other than heavily suggest the new stuff. A part of that is another protocol called the Inter-Control Center Protocol. This is the protocol that's used to communicate between control centers and support wide area management. That shared the underlying protocol that's underneath UCA in 61850, which is the manufacturer's messaging specification, MMS. For the underlying bits on the wire encapsulation. And that is now a separate standard. So all these standards finally led us to a point where we have some standards available to us for field device communications that have a concept of standard names for standard things, an information model that's vendor independent. So when I buy a device from vendor A and vendor B, both of them, if they want to represent voltage, the same name string is used to reference them, regardless of how they're mapped internally to what kind of processor they're using or memory architecture, what have you. And that was a big deal for the for the utility industry. That just shows the mapping. I'm not going to go through that. So what's so great about this? Basically what no other utility protocol had before 62850 came along is we now have the ability for self-description, because in addition to standard names for standard things for the data itself, we also have standardized the ability for the metadata. We can retrieve the information about what units are represented. We won't have the Mars lander, problem. We can go and ask the system and is this, what are the units that we're getting this from? Is it volts? Is it kilovolts? Is it forlongs per fortnight? Okay, so we're able to represent those in any one we want, but it's discoverable. Instead of, we're dealing with structured data now. We're dealing with data that is derived from common classes so that we can reuse various classes of data. A lot of very fundamental concepts of information architecture, we take advantage or take for granted in most other industries, but to the utility industry, bringing together the power engineering world, just trying to keep the lights on, with the communications world, it was a big deal. So a number of capabilities were made available to us. The ability to replace traditional point-to-point copper wiring to interlock one protective relay from another with being able to do that over an Ethernet network. Being able to transmit waveform samples in real time. So instead of having to put a current sensor and run copper wire to every single device that needs that current information, we can put one sensor in, digitize it, and make it available to a whole rack of equipment that can see the exact same data without having to duplicate all those analog sections and the costs associated with that. So a lot of really good things. So in general, the main things that are different, we have object models, we've got the nouns that the protocol operates on, we've got application services, an abstract communication service interface that helps us with this layered concept, technology layering and abstraction and loose coupling. And then underneath all that, we have the profiles, that can change over time. Today, we may be using MMS as the underlying protocol to instantiate the abstract service interface, but we also can use other protocols underneath that, new profiles as they became available, more readily available, have additional features that we want to use. We can map them without affecting any of the stuff higher level in the stack. When we talk about 62850 particularly, it's a suite of protocols, not just one. It took a lot of years to develop all the different parts, but we've got sampled measured values and generic object-oriented substation events that basically operate directly as their own ether type. They bypass the rest of the stack because we're dealing with sub-millisecond performance requirements. The difference between a substation responding to a car hitting a pole and causing a short circuit and making sure that that transformer is simply de-energized rather than blows up, maybe milliseconds. And so some things were done to support very fast connections. But for the bulk of the work, using the MMS protocol suite with TCP/IP profiles, allow us to provide communications and take advantage of all the infrastructure that we have in front of us today to deal with TCP/IP-based traffic. So in a typical substation, we're dealing with intelligent electronic devices that are connected to generally two buses, what we call a station bus that's used for just polling and reading the various data from these devices, controlling them, opening and closing breakers, reading settings back, changing the settings of protective relays, and then a fast bus, the process bus, that may be receiving the high-speed sampling from those voltage and current sensors in real time to that drive the way that the sensors all work, the IEDs work. So the standards associated with that, standards associated with the fast side of it, the time syncing. Time syncing has turned out to be very important. One of the things we learned in the 2003 blackout is that without time stamping, we couldn't really figure out exactly what happened. So since that time, huge driver and value has been associated with trying to get the time stamping right. So the protocols are all based on existing standards. At the high level, the application layer, the object models, again, the standard names for the standard things, that's where the technology-independent interoperability comes from. That's what gives us the vendor independence. It isolates us from technology change at the lower levels. When I first was implementing this, we were implementing this on 10 megabit Ethernet. Everything works just fine with gigabit Ethernet. Works fine over fiber, wired, what have you. That benefit of layering comes into play. All right, I'm not going to go into the incredible details here. So what can you do? The services provide the ability to name objects, to read and write them, to describe them, to be able to report when information changes, to log data, to do file transfer. So we have this thing called a logical node, which is just basically an object, and it instantiates one or more common data classes. So some very classic computer science, things that are very come natural to an information architect, but were new for the utility industry. But we were able to do this in the early '90s, which for the utility industry was, looking back on it, was a pretty big deal. The abstract services isolates the data from the specifics. We can map to many protocols, handle the future, the future proofing. Let's see. So the data objects represent all manner of things. I talk about voltage and current readings and the like, but all manner of sensors, control inputs. It can be represented pretty much, anything that we've historically done with mechanical devices and standalone electronic devices. We've been able to use this, this protocol to address. Everything it comes down to the name. So you can think of 61850 to some extent. If you look at the naming convention here, it has a lot of similarities to an SNMP mapping, a MIB. It's a hierarchical representation of a device. The farther down you go, the more specific you get. So here we've got a top-level device that may be an addressable device. This is a name for the third instance of a device that does measurements. Then we can get down to the phase voltage, one channel, phase A. It's the absolute value of the magnitude and the floating point representation of it. So very just like you drill down into a tree in an SNMP type tree, similar kind of thing here. I hadn't really thought about it before, but 6150 could be thought of as SNMP on steroids, I guess, if you will, from a naming point of view. All right. Okay, the other element here is the immunity I mentioned earlier. Getting all of this to work in a substation environment is a real challenge. A lot of work has gone on to be able to support that. We now have standards in the IEC that define exactly how this equipment needs to behave. In these environments, in high electromagnetic interfering environments, things that those of us who've created hardware before, products for the corporate environment, never really thought of before, and it's a real challenge to get this stuff to work in these harsh environments. And it's harsh in many ways. We've got wide ranges of temperature, but also, as I mentioned, we have a fault occurs in the system, high current flows. These electromagnetic environments are significant. Security, of course, is a major issue in supporting these systems. So once we have communications, we have the ability to control large amounts of energy. There are clearly security concerns, security from a safety perspective, as well as from a disruption to commerce point of view. In the early days, the systems were standalone. They were barely interconnected, and the utility communications world grew up thinking that security by obscurity was the way you achieve security. And it has taken us a very, very long time to address that. And I would say that the problem still isn't solved, of the institutional problem of security. We still will run into engineers who say, oh well, that's no one knows about that protocol, and as anyone who knows anything about security knows that is not a way to secure a system. So a lot of work is currently going on to address that. There are several standards that have been developed recently, particularly in this particular standards arena, to specifically secure these core standards that are most pervasively deployed. TASI 2 ICCP, the Intercontrol Center Protocol, 61850, the European versions of DNP3, which is IEC 102 and 3 and 4, another related one, 870, and then DNP3. So we've managed to create some standards to address the security on these relatively new protocols. Some protocols are considered not worth it, Modbus, so it's not being addressed. The utilities, do take seriously their overall security architecture, and almost every utility is different because of how they evolved, how their infrastructure evolved, whether they have a fiber optic rings in a nested SONET ring system, or they just got a few microwave point-to-point links. It's all over the map as far as what their physical communications infrastructure is. But regardless of how they've done that, they're applying best practices that are evolving for utility SCADA system protection, involving what you would consider as standard practice in an enterprise environment, but with some very special needs. Recognizing the importance of the energy management system, the SCADA network, for which the wrong button pushed on one console can black out an entire city or large area. Particular attention is made to ensure that it runs on a completely separate, physically isolated network in most utilities. In this case, it's depicted by the blue lines and the blue ring, versus the corporate firewall. In this case, the red ring, and with a lot of monitoring in place and mechanisms that allow specific corporate clients to access aspects of the energy management system so you can do your work, but through some very controlled environments. And there are as many versions of this diagram as there are utilities, and some utilities have multiple versions of that. We have a number of guidelines in the industry that are driving that. The one that most of you hear about are the NERC SIPs, the North American Reliability Corporation, responsible for the critical infrastructure protection standards. But those standards focus more on accountability and who to blame when something goes wrong than to give a whole lot of guidance on exactly what to do. So other activities are going on to develop things like what NIST is working on here now, on this recently released NISTer, providing specific guidelines on how to secure different elements of the smart grid. So these architectures will evolve, common elements, things that work will be identified and deployed elsewhere. But a common theme in these architectures for what we've had out in the field for a very long time now is our critical devices that do the bulk of the switching of energy, and where a lot of energy is concentrated in a small place, and if things go wrong, can result in loss of life, loss of millions of dollars of equipment that may take a year to replace, is all at the substations. The issue is that these substations oftentimes are shared facilities. They may be a transmission company like a Tennessee Valley Authority may have their equipment there, but it's shared with Bubba's Co-op that has 2 employees and 700 customers, and the facility is accessed by any number of people. So even in that environment, we have to treat these as if it is an unsecured facility. We cannot trust any of the devices that are in that system. So our trust no one motto here. So there's been a lot of discussion recently in for smart grid and home area networks. Well, how do you if the home area network device is somehow connected to or interoperating with a utility, the utility network, isn't that a risk? Shouldn't we just not do that? Air gap it, if you will. Well, I mean, we were able to accomplish that with point of sale terminals, ATMs, both of which exist in untrusted environments. Anyone can get their hands on one and tow one away if they want to. But we're able to apply the standards and security technologies in order to be able to deal with untrusted end nodes. So what really bothers me when people talking about trusting the end node, and that's the wrong statement. There is no such thing as a trusted end node, even in this case where the consequences are much more critical than a home area network scenario. So it's a matter of having that mindset and designing the security to address it. All right, I'll get off my security soapbox. A key thing that happened in the early 2000s, starting around 2000 and culminating in 2002, to help get the utility mindset to start thinking, even further about structured information management, was the EPRI IntelliGrid architecture. Historically, in the electric power utility back office, did a lot of one-off integrations. You would have one engineer develop and one team develop software for managing energy markets, another for, let's say, meter reading, another for SCADA. Say someone found that there's some value in gluing these things together. So you would do a one-off implementation, get the guy in the cubicle next door whose kid knew Visual Basic to write an application. Any competent engineer, or your neighbor's kid can write a VB app to, glue the two systems together. But trying to do that in a way that's extensible, manageable, maintainable, and secure is another story. So there's a lot of systems that have been developed where you wrote some code, extended it, then you had to write a little bit more code to extend it again, glue it together. You're taking less and less use of the interfaces that these devices present themselves. And sooner or later you run into something that you can't bolt on, like security. And what the IntelliGrid folks project did was to really begin to make the case, evangelize. It's sort of one of my jobs, to evangelize to utilities to use this kind of approach, to evangelize, getting them to architect the system from the beginning, create an infrastructure that has security, data management built in. And so we've created a series of standards now to support this concept of standard names for standard things in the back office. We have a reference architecture that's been identified to codify all of this within one of the IEC committees that's responsible for telecontrol. So we have identified various standards that deal with the information encapsulation at the high level and through middleware, web services, a common information model for the enterprise. Then getting into recognizing the various application domains that we have to support and the unique requirements associated with them, recognizing that all of these applications require on data acquisition to sensors in the field and control and actuators in the field, for which we've identified a variety of standards in our reference model that meet the disparate requirements of these different applications. The utility enterprise is a very large enterprise. It encompasses almost every kind of back office business model that you can think of, in one place. And the requirements for the field devices cover an incredible wide range. From if you get me the data once a month, and if I'm missing some data because it's accumulated, I can fill in the blanks. That's metering on one end. Or, by gosh, I need 4-second data, absolutely reliable, because I got to feed a state estimator, because if I make a wrong decision, I'm going to knock out the Northeast. So we've got a wide range of requirements. And the various standards that have been identified in the reference model address those various needs. This is but one reference architecture of several others that are really necessary to visualize the information exchanges in the utility enterprise. It's one of the challenges we have in front of us is to try and find a way to come up with a comprehensive reference architecture or an architecture of architectures to represent all the different information exchanges and business operations that need to occur. A lot of ways to look at this. So basically what utilities are now moving towards, the rest of industries have been doing this for a while, but service-oriented architecture is relatively new to utility enterprise. But we now have standards that are codifying the service-oriented architecture type adapters and interfaces, codifying some of the enterprise service bus characteristics that are necessary to support this service orientation of the utility enterprise. Translate that to a real example. Southern California Edison is just about to publish this. as their overarching architecture, showing some of the elements. They've got their field area network, IP-based connectivity using 62850. 62850 and IP again here with their for protection and control networks. IP being used in many of these other DNP3 over IP, 62850 again. Having a common services environment that has security built in, intrusion detection built in, intrusion prevention built in, being able to recognize and utilize all manner of networks, use WiMAX where necessary, fiber where necessary, being independent of the underlying physical layer manifestations. And then recognizing that we need an enterprise architecture in the control center that can deal with all the different types of applications, energy management systems, GMS, outage management, distribution management. I mean, there are hundreds and hundreds of different application categories that have to run in a utility environment. So that's, we're starting to get the early adopter utilities to start thinking in terms of architecture, creating a reference architecture that they can build and design to identify their well-defined points of interoperability for which specific standards work today, but they can change them out and put new ones in later because they've implemented the very basic concepts of loose coupling and layered systems. So just to revisit the picture, in this short amount of time, I've really only been able to talk about just a tiniest subset of these. Talked a little bit about DNP3, 62850, ICCP, the common information model, again, standard names for standard things at the enterprise level. We're using things like SOAP and web services and RESTful implementations as well at the enterprise level. The common information model with XML encapsulation of the data to run our various business applications. All of these, we've been doing this for 10 plus years in one form or another. And there's been a continuous evolution, more exponential here recently because we're starting to get a lot more uptake on it. So this work is pretty mature. We now are able to be totally agnostic of what's in the wide area network. We've got all of these technologies are being used because we're mainly using IP. We can use whatever is cost effective in our particular area. The Wild West still exists right now in the utility industry in the field area network, the last mile, if you will, or last several miles to the end devices. This is still the area where it's driven by vendors in a very vertical market where it's primarily proprietary. The well-defined points of interoperability are here and here. We don't have MAC-PHY layer interoperability or even another layer or so above that in this arena. So that's something that people are working on. The value just hasn't surfaced yet completely to force that to happen any quicker. We also have evolving standards that are still being worked on in the Society of Automotive Engineers for the electric vehicle. Got the connector nailed. Some issues with the with the fast charging connector because SAE neglected to pay a whole lot of attention to little things like UL and some other standards they should have. But that'll be addressed. But the big problem here is these guys don't have a whole lot of domain expertise in understanding what's necessary for demand response and other managing that load and doing smart charging. So we've got a lot of work to do here yet. We've got a lot of proprietary things happening in the asset management area. There's a lot of asset management systems out there, but they all roll their own thing right now. So there's some work to be done there. In the consumer side, we've got dozens of protocols. We have an interesting email exchange going on right now where I was able to relate that I've got I've got all of these and a dozen more running in my home automation system, all using gateways. It's very expensive to integrate that way, but we can find we can make it work. But there's work going on to try and at least agree on the information model. Again, if we can get to agree on the standard names for standard things aspect and map it to any technology, that will be a good thing. And on the distributed resource side, again, we don't have a lot of, we have some standards that are based on 62850 to represent the data, but we're missing some electrical standards to ensure that the safety of the network is provided for when we have pervasive deployment of these things. We need new protocols that can interact between a photovoltaic panel that's generating energy back into the system and the protective devices I talked about that are on the substations, so they know when we're generating. And if something happens on the line that we have a car knocks down a pole and we've isolated the system, that we are able, that the line worker knows that that part of the line is in fact dead, so they can work on it safely. So a lot of things have to be done from a protocol point of view there, and we fully expect TCP/IP, internet-related protocols will be involved in coming up with that solution. So a lot of work yet to do, and this is also just scratching the surface of probably the most visible standards that are out there. But again, IP is everywhere. I mean, IP is involved with almost all of these, not all of them, but almost all of them. Okay. So why did so some people ask me, well, why do we have this mismatch of things that is out there, and how did they evolve the way they did, and why is the uptake on standard protocols and the like taking so long? And the key is really looking at the drivers for utility automation. The bulk of the decisions are all primarily the first, second, third, fourth, maybe fifth thing are all safety. Line worker safety, public safety, and safety of the equipment. The equipment that we're dealing with here is massive amounts of energy are flowing through it, and some of the equipment literally takes a year and a half to build. In my early engineering career, I worked for Cooper Power Systems in McGraw Edison, where we built the 500 kV and 765 kV transformers. From beginning end to end, it takes a year and a half to build one. Okay, so you go to extraordinary lengths to prevent from having one of those fail. There's only a few spares in the entire country. You don't want so there's it's a lot of attention has to be paid to that. Reliability, just keeping the lights on. The U.S. has probably the most reliable electric power in the world. As much as we talk about aging infrastructure and the antiquated nature of things, it's still a pretty reliable system, because of the distributed decision making that's done, the mechanical relays as well as the new ones. So the next objective is to optimize for reliability. So a lot of redundancy, a lot of cost. Being the tight coupling was considered as a way of managing some of that reliability. The security in the utility world, you hear people talk about security. Security has a different meaning to a utility engineer. It means really the ability to meet demand. And be able to meet the future demand is what security means to a utility engineer. For all of us information geeks, we think of cybersecurity, but we have to be able to address both. Stability, being able to deal with the load generation balance in real time. These protocols are designed to recognize that without a major breakthrough on bulk storage. In general, the bulk of the utility system, we deliver energy in real time, millisecond by millisecond, trying to maintain that balance. A lot of decisions are made, a lot of requirements are driven by that real-time nature of things. Only when you really get down to getting near the end of the list, is it for convenience and for making it easy for end users to be aware of their energy consumption, and to make it easy for vendors to participate in a market. That gets lower on the list. I put regulatory at the bottom just because I hate regulation, but a lot of things are done because the utility has to. There's a fundamental concept of the obligation to serve, universal service. So things that you might say, well, why can't we just apply this technology and then automate it, and just require that we have a gateway in the home and we've got PCTs and then we're done. Well, we can't do that and mandate it across all socioeconomic classes, and put requirements on the end user, to do that. So one of the reasons the utilities end up getting inside the home area network network is because of that universal service requirement. It's not as if they want to be able to get into the home area network and provide thermostats to an end consumer, but in many cases they have a regulatory driver to be able to do that. So there's a lot of unique drivers that exist for for a utility. One thing that I wanted to get across is when we have a failure in a router or in the internet, we inconvenience someone. I can't run that Google search right now. I'll have to do it a little bit when the network comes back up. May lose a transaction or two. Someone may lose some money. But when we're dealing with the electric power infrastructure, we have physical manifestations of these errors and issues that we've got to be able to deal with. So when things go wrong, we cause lots of noise, lots of heat, things that have real physical manifestation as well as cost associated with them.
It got really bad.
This particular failure that is continuing to burn because those protective devices I mentioned failed to communicate with a neighboring device. In this case, because of misconfiguration. Then the second contingency upstream from that communication didn't occur, so the backup protection failed. And resulted in the tertiary protection having to coordinate and finally clear the fault.
There it goes. There goes our power.
And there it goes.
That was beautiful.
So part of the the other aspect of things, we prefer to do things remotely when we add communications so we can prevent things like this from happening. Again, a failure of a mechanical device that's being operated locally can have catastrophic effects on human life as well. He was okay, but here you hear the car alarms going off in the background. This is a relatively small fault, but a significant electromagnetic pulse disrupting equipment in the air, in this case a car. This kind of thing happening in front of your house doesn't exactly give you a warm, fuzzy feeling. Again, when a failure occurs, our protection doesn't work, communication goes down, things like that, happen. They're on a small scale, they're on a large scale. That line probably was out for, a couple of weeks replacing all the insulators. Here's another example where the protection inside the facility failed. It never cleared, and in this particular case, we have a rather spectacular failure of a large transformer, and that took many months to replace that. So when we have a failure in the communications network and the utility infrastructure, there's real consequences, and that's why every industry says they're special and they're different, but there's not too many that have those kinds of consequences, and that's what why we pay a lot of attention to very carefully and deliberately adopting new technologies moving forward. That's it. Any questions? Go for it.
So you mentioned IP a lot.
Yeah.
IP is one of those protocols that has a built-in number scheme, which means there's essentially a sequential rev, or at least point-to-point rev. There's all these opportunities for things to go wrong. So I'm wondering, have you actually considered prodding the people who developed TCP/IP?
Word been good.
But have you considered prodding them so that you don't have to use arcane and difficult to use protocols like BGP in order to go from end node all the way to somewhere else?
There's a lot of folks in the utility industry who point to TCP/IP and say, man, we could do a lot better. But with all the failings and known issues and vulnerabilities, we've managed to engineer systems around them to be able to address and deal with a lot of those issues. Yeah, absolutely would like to solve some of those very fundamental problems. The issue is, well, who, how much money, is it worth it? The utility industry learned a long time ago, we don't want to do another one-off. We want to use what's pervasively deployed. So pervasively deployed infrastructure that has known flaws that we have workarounds for is better than a new approach that fixes the known ones, but now we have a whole host of unknown issues and flaws. So that's sort of the trade-off.
Send this man a nice email.
Believe me, we'll talk about that. So, yes.
So during the California energy crisis, one of the big issues was this keep the lights on phrase, because the government couldn't distinguish between somebody who really liked the air condition at 68 and somebody running a heart monitor. Is there anything in this that leads us to being able to selectively shut down devices?
Yes, I mean, the newer technology being deployed will give us that the capability of doing that. By most of the utilities have a good enough customer information system. They know where critical loads are. But up until recently, when with those smart meters with integrated disconnect, the best we could do is disconnect all the load at a substation. So we go into rotating blackouts. We got to shut a whole substation down, meaning all feeders, meaning fire stations, police stations, people on life support, as well as all the folks who are just watching their plasma TVs. That was the best granularity we have. With smart meters, with integrated disconnect, we can do that. But of course, we have a large faction of folks who, think the fact that the ability for a utility, for some reason they relate the utility to government, but being able to first of all determine what your usage is and whether it's critical or not, and then be able to turn it off is a big brother issue. So we have political and social problems to solve to be able to allow us to use the technology that's presenting itself.
These smart meters, are they per house or per device?
Per house, probably per house. So basically on a household by household basis, instead of going and shutting down the entire entire substation, we could go and send a signal to turn off the disconnects on all the houses that are not, that don't have a medical exemption. Turn off all the. We can keep all the grocery stores, the convenience stores in the neighborhood on. We can keep the police station, fire station, other elements selectively, all energized, and accomplish our objective for reducing load for peak management.
So my thinking was, just looking at my house, there's very little power that gets consumed at any one time, except for the dryer and the stove. So I'd prefer a system that just came in and its first step was turn off everybody's dryer and their stove.
Well, that's exactly the next step. See, the first step, just takes the what has classically been within the scope of the utility, the service to the house, and let them control that, which has high benefit. The next step is allowing the utility to be able to send either a price signal or an emergency load control signal saying, for any appliance that knows about it, that is able to hear me, go ahead and defer the defrost cycle. Go ahead and shut the dryer to tumble so we don't mess up the clothes, but don't turn the heating element on. We have the ability to do that, but again, there are social and political questions as far as how much into the home should the utility go. Where does its responsibility end? Should it just provide the information but not be concerned about how the information is consumed internally? Well, you could argue if they don't have some visibility into and not knowing what's responding or not, they can't manage the system. So a lot of social and political issues to be addressed on that one too. Yeah.
On your diagram near the end of the smart grid, you showed the home and the car connecting up through the utilities private network. Do you see it as also equally viable for the home and the car to connect through regular internet connection?
Absolutely. The field area network is generic there. That field area network could be one or more private networks by a third-party aggregator, a utility, the internet. It doesn't really matter. And how that's managed depends on if that consumer is subscribed to a special utility rate program, in which the utility needs to be assured that the signal has gotten there and they're meeting the terms of the contract, for having a special rate for responding to a load control signal. In the ultimate, if we had nothing but pure real-time prices, so we delivered pure prices to devices, you don't have to create artificial programs that require a two-way acknowledgement of whether, did you do this or not? Well, if you didn't respond to the price and stayed on any out, more power to you. You paid through. But if it's a direct load control program, you want to make sure, the utility wants to make sure that they really did respond, didn't put foil around the radio and prevented, the device from being turned off. So again, you got, some social issues that have to be addressed here on rate reform and the like. Yeah.
More on the same topic, how far away do you think any realistic solution to this problem is? I mean, there's a whole bunch of different solutions to this problem that you're talking about. There's ones where the utilities push prices and then, people can opt in and act voluntarily. There's ones where the utilities can go and control devices in your home and smooth the peak power. It can make everything a lot more efficient. And potentially there's economic incentive if they set up the right kind of system with the energy markets and deregulate them. Maybe people can opt in and partake in the profits from turning off my air conditioner in the middle of the day because it's too expensive and so forth.
Right.
And I can give that power back to the grid and get paid for it maybe even.
Well, technology is not the problem. We got a lot of ways to do it. So there's we've been implementing demand response. I implemented my first demand response system, like 30 years ago. So the concepts have been around a long time. What's making it more feasible now is that technology is cheaper, ubiquity of communications, multiple ways to do it. We're creating architectures that realize that just codify the information, don't tell me how. But the rate reform is a key element to that, to make sure that we can have a mechanism where the true cost of energy is actually represented. So there's an incentive, a business incentive to do that. And that just takes time. And we have a situation in the U.S. where every state has different regulation. It makes it difficult for a national or international market to develop to produce cheap equipment. So there's a lot of barriers, and most of them are not technical. I mean, we got plenty of good technical problems to solve too, but they're less daunting than some of the rate and regulatory issues.
Well, I guess maybe part of the question would be is if people aren't doing it, there must not be a real need, right? Like the lights aren't actually going out in my home. I can run my air conditioner in the middle of the day. So while we'd like to change the peak load and it would be cheaper for the utilities and they'd make more money, it's not clear what benefit there really is to me at this point.
Well,
how far away are we from really caring about that?
Well, the business case is very difficult. In California, it's a lot easier. Your rates are high for all sorts of reasons. Your capacity is constrained because in California and other parts of the world too, but in California in particular, it's difficult to get approval to build anything new. NIMBY is and Banana, you build absolutely nothing anywhere, anytime, are huge problems. But the energy demand is still increasing. California has the lowest energy demand per capita in the country, but it's still going up. And if you're not allowed to build anything, it makes rates go up, and we have to use this technology to manage that peak load. So there's a lot of drivers. If we can't make it here, we're not going to be able to make it work anywhere. Where I'm from in Tennessee, be a long time before I see that. I pay 6 cents a kilowatt hour. We have no congestion problems. So I mean, even if we did have a 5-to-1 price difference, I'd save $1 or $2 a day.
Why isn't the better solution? Like why build a smart grid? Why not just build 3 nuclear power plants in the middle of the state somewhere and increase the generation capacity?
Hey, it's like I said, these are not technical problems. These are socio, political, economic, issues more than anything else. Good question.
I mean, we're a bunch of geeks, and we think it would be neat. Google even has some program where you can install continuous metering on your home and get all these real-time updates.
Yep.
Somebody who has access to that
because
data
you can.
Figure out if
right.
you're using a hairdryer or not.
That's right.
And so I actually think the privacy concerns are legitimate. People who hack into these networks, and if you build them, they will hack in. So people will then know what you're doing, and if you're home, and I think it is a kind of Big Brother problem, and so I feel like people are kind of right to resist the technology until there's a real benefit.
You hit the nail on the head with a lot of these questions. That the core for many elements and aspects of smart grid on the end consumer side is consumer empowerment, providing information so that you can make more informed buying decisions. It's really not much more complicated than that. We have the technology to do it. There's way easier ways technologically for adversaries to find out your living patterns and the like. And there are ways, like we've managed to secure ATMs and point of sale. We can do a pretty good job at securing it. Not going to prevent every issue from occurring, but that's a matter of managing risk. But is it worth it to provide the information to the consumer to save some amount of money? What we found is that end consumers don't want to be energy managers. After the first couple of days, that nifty display and watching your energy use on your PC, the novelty wears off pretty quickly. But if you do have pure prices to devices, and the devices are smart enough just to simply listen, and when they can make an intelligent decision, and you save a few bucks because you didn't have to do anything special, that has some value.
Yeah, no, exactly right. If I could install something in my home for $100 and have a deal with the power company where I pay $20 less a month, and in return, it pays for itself, but it also gives the power company some limited ability to manage the power load that my home draws at certain times. I mean, I think people would install that. But I mean, no one's doing it. You're right. The technology's existed forever. I'm just trying to figure out.
And in the regulated environment, I mean, it's not as if you're saving the utility, any money. Sooner or later, any costs, sooner or later, any savings, sooner or later, are reflected in the rates. So, just given your time window for the rate cases, the consumer pays no matter what. What we've been able to demonstrate that smart grid's able to do, it makes it suck less. In other words, basically, energy supplies continue to cost more. More people are using, so demand is going up. We can't build anything. That has price pressure goes up. All that smart grid can do is make that suck less. It can make the prices not increase as fast. Now, a lot of folks, don't. Don't want to say that. It's everyone expects smart grid to make things, go dramatically down in price. Well, for some individuals who are making, stupid decisions because they didn't have any information, probably can save a whole lot of money. But in the grand scheme of things, I fully expect energy costs to continue to increase. Just with smart grid and this technology, they'll go up a lot less fast. Yep.
I had a question on the other side, which is the generation side, and I'm concerned about variable sources like solar and wind that are unpredictable, and then also home generation, which is probably also unpredictable. And feeding all that in, and keeping the state.
Yeah, we call it variable generation and renewable variable generation. Some of it is very predictable. For example, we know solar panels are not going to produce energy at very well defined points in the day. So there's some things you can do. Actually, in bulk wind, with the weather forecasting, with a tightly interconnected grid, it's more deterministic than you would think. Even with bad forecasts, for one wind turbine, I can't predict it. But in the Midwest, all interconnected together, I got a pretty good idea and can predict hour by hour pretty well what it's going to do. The thing is, turns out load is way more variable and unpredictable than some of the generation sources are. We just published a study called the Eastern Wind Interconnect Transmission Study, EWITS, that demonstrates what we need to do in the eastern U.S. to get 20-25% wind integration. And some new transmission is needed in order to couple things together tightly enough to manage that variability. Storage obviously can come into play, but a lot of folks talk about, well, let's locate battery storage at each of these variable generators. Well, that doesn't work all that well because the bulk of the variability is in the load. And it turns out that storage is always good, but it makes more sense to analyze it as a system and figure out where the optimum place is to put the storage where it can most cost effectively be used. So that's something that we have to look at is how do we architect the system to support thermal storage, electrical storage at appropriate places of the grid to handle higher and higher penetrations of those types of generation. But it's not an easy solution.
So helping you out on the load side, I'd be willing to have a dial on my dryer that says, start whenever the power company says it's a good time to start.
And that's exactly what we're talking about. We're talking about smart appliances, smart devices. That's some of the work going on in the standards organizations here today is to figure out what is the information that we need to get to an appliance to make that kind of a decision. A dryer manufacturer or a washer manufacturer does not want to have an external device turning something on and off because you got a consumer consumer interface problem there with destroying clothes. So tell me when the price is high, or tell me when there's a grid event, and let it make the best decision on do an orderly shutdown or just keep things tumbling but turn the element off. That's what we're working towards, is develop the standards on how to encapsulate the information so that those appliances can be built. Because you don't want to have to program it. We all know what happened with the VCR and your programmable thermostat. The thermostat's on hold all the time. Okay, and a survey demonstrated that maybe only 20% or less, 15% were actually being programmed. And you got to get the person out of the loop.
So if and when they build a system like this for utilities, kind of giving the informational messages about the state of the grid and the price of power and so on, do you think they would deliver this over some kind of broadband on the power lines themselves, or do you think they would use the internet?
It'll be delivered on whatever makes sense in that particular area and is cost effective, and can be relied upon to be secure. Initially, because of the investment that's being made for smart meters, we need smart meters to reduce, we need to replace the meters to capture the interval data so that we can have innovative pricing. And it turns out that by putting the smart meters in place and putting that integrated disconnect, we get a whole bunch of value by being able to do that selective rotating blackout, to be able to save a pile of money on new homes and move-in, move-outs and the like. Coming along with that is a communication infrastructure that allows us to deliver some data that way. So early on, demand response signals will likely be delivered over the utility network just because it's available and an obvious thing to do. But you don't have to. You don't need advanced metering infrastructure, smart meters, to deliver prices to devices. There are other means through other external networks, broadband, to deliver that. The thing is, you got to find a way to do it in a way that you can trust the information.
Verification of the consumption at the end, right? If I agree to turn off my air conditioner and take a payment, then I need to turn off my air conditioner.
Right, and that's the difference between the program approach, which is that you struck a deal. I'll do this, if you do that, and now it's got to be audited. That's what we call that's an energy, a demand response program. If instead you simply, there were prices for hourly prices. If you choose to use energy, when the price was high, so be it. We don't care. There's no contract. We're charging you for the cost of energy. You don't have a program, so you don't have to verify it. We need to measure your energy use, but we don't have to be aware of all the devices and how they're behaving and auditing your behavior. The prices get adjusted, to influence the behavior, and over time you figure out what those prices need to be and let the market decide. We're a long way away from that, though.
Has anybody thought in terms of the privacy problem? Has anybody just written about or discussed protocols? I don't know, kind of like cyber cache, where you can probabilistically enforce the rules across an ensemble of people, such that any individual's privacy is protected, but at any given time they might have to offer up some proof, and if they fail, then they pay a high penalty.
I'm sure. I'm not aware of any specific ones that are going on. There's a lot, but I'm sure there are some folks looking at that. Fundamentally, from the privacy, point of view, the utility always has, and still does. If they want to go look in the data, when when you're using energy or not. With a smart meter, they simply know it can know it to a higher degree. And it's no different than your credit card company being aware of every transaction that you make, if they choose to go and look at it. So there's a stewardship of the data issue that's required to support that privacy.
There's also, this is sort of the thing that Google faces in some respects. When you have automated systems that are collecting data and putting them in a central repository that can then be searched and mined by computer programs.
That's right.
There's actually information you can discover there that you couldn't before.
Absolutely.
And I challenge the meter readers to collect enough data to learn the same kinds of facts.
There's huge value in those data sets that could be mined, but this is where policy is required. This is where, as already exists in the banking industry, especially the credit card industry, to what level they're allowed to mine that data for marketing purposes and provide that to other vendors. That's something that probably I'm not a big regulation guy, but that's probably something that makes sense to have some rules on. And I fully expect to see that in the utility world as we have that more granular data. All right. Went a little bit over time there, but thank you all. Appreciate it.